Okay, so hi everyone. All right, so remember we had this MG, so closed, connected, Riemannian manifold. So then we attached to this spectral zeta function of M. So we denoted this by zeta ms. This was sum 1 over lambda I to the power s. Lambda I is different from 0. And this series by Wiles' law, it's immediate that this is holomorphic on real part of S bigger than a dimension of M over 2. And then we used heat kernel expansion coefficients, some of them, to get some more precise information about this. There is meromorphic extension to the whole complex plane, and we noticed we proved one crucial property, which is this function, once it's extended to the whole complex plane, is always regular at s equal to 0. So showed that this guy is regular. I mean, it's holomorphic at s equal to 0. Okay. So now today we are going to use, as Reisinger did, to use this holomorphicity, regularity at s equal to 0, to define a quantity which is called determinant of Laplacian. So definition. So let us define log det prime of Laplacian by minus zeta prime at 0. So you take derivative of zeta at 0, which we know exists, and this is log det. So the det itself, again, det prime, is exponential of course, minus zeta prime. So the idea of prime means we are taking product of all non-zero eigenvalues, because here only non-zero eigenvalues appear. If you want to take 0, because in this case 0 is always in the spectrum, then you get 0 also means non-zero eigenvalues only. So morally, this is that prime. We are claiming that this is a replacement for product of lambda I over I. Right. So, of course, the first thing you have to notice is that because these eigenvalues are going to infinity, this product is divergent in the usual sense. It's badly divergent, in fact, in the usual sense. It's never ever convergent for manifolds. So to say that this is product, in other words, this is basically determinant of this operator whose eigenvalues are these positive numbers lambda i's, we have to say something, we have to justify this. So there are different ways of justification of this formula. The simplest, easiest is the following. So justification if you want. In fact, you can notice that if you just take finite number of terms, S, right? From 1 to n, let's call this zeta n ms. So it's cut down up to n, right? You just look at the first one, first n terms. Then this function, of course, it's holomorphic everywhere, right? So this function is holomorphic. In C, it's an entire function for any finite number n. And then it's very easy by taking logs on both sides. You immediately show that this, in fact, product of lambda I from 1 to n is equal to minus zeta n prime m at 0. So in other words, if you take derivative of this finite sum, evaluated as s equal to 0, you do get indeed, you do get indeed exponential of minus zeta n prime m at 0. Log of this is the term that we introduced, right? So this is elementary, of course, and sort of justification is that, okay, you're saying that zeta ms in some sense is limit of, as n goes to infinity, of zeta n ms in some sense. And so we are thinking of, well, I mean, you're thinking of lambda I, I from 1 to n. This, as n goes to infinity, it goes to this quantity. But in reality, it's going to infinity. So this doesn't have a limit. But let's assume it has a limit. And then you change this term by this term. And then you use, I mean, you kind of justify by using this sort of identity. Then you replace this by the limit value, which is this, and you arrive at this one. So that's, but of course, this is complete hodgepodge. I mean, this is no justification because this quantity is not well defined. So this is very easy. This is quite easy to see that this quantity is not well defined and this definition is not solid in that sense. However, what is very, very difficult to understand and to think about is that nevertheless, this concept is extremely useful in mathematics and physics. This is not easy to understand. So, the point is, I'll just write it here, but why this regularized determinant, I'll just write it like that, is so useful. Of course, you can say, well, I haven't seen any use of this. What use? This is just a definition. Someone else may come and give another definition. Yes, I will show you some applications as we move on. So, okay, so that's the subtlety of this concept. This is a concept of much more advanced stature compared to more elementary facts of analysis. So I don't think I want to say more. Just one more comment I should make is that there are other competing definitions to replace this infinite sum, infinite product by a finite number. There are other competing definitions. I will mention one of them later on. And in fact, there are different regularization schemes that one can use. So whether they match or not is an interesting issue. In some cases they do under some conditions. In general, they don't. And this is the whole industry of regularization. So we will see some of those later, but not now. Any questions? Okay. So now the first thing to do is to look at some examples. So I will give a series of examples. So let's take m equal to r mod 2 pi z. So this is a circle of radius 1. So in this case, the spectral zeta function is actually, as we saw, is related to Riemann zeta function, to original Riemann zeta function. So in this case, zeta m, as we calculated this is equal to, all right, so this is sum 1 over n to the power 2 n squared to power s. This was n different from 0. So this I can write it as twice sum 1 over n to the power 2s, right? So n from 1 to infinity because of symmetry n minus n. Okay, so this is twice Riemann zeta function at 2s, right? So this is originally convergent for real part of s bigger than half. For Riemann, it's just s, it's real part of s bigger than 1, but here is real part of s bigger than half. Then all we need to know, so the conclusion of this story is that zeta prime of s0 is known if Riemann zeta function 0, zeta at 0 is known. Right? So if we know this, the value of the derivative of the Riemann zeta function at 0, then we know this. Okay, so you can just differentiate this easily, and then there's a 2, so 4 times this one. So that's easy. So now, but how to calculate this? So the question is, what is this number? So as we will see, this calculation actually is not very easy. I mean, in all these calculations, explicit calculations, you have to pull out something very deep and analytic, and something very, very special is happening if this is going to be done explicitly. So in this case, the calculation is based on several things. Actually, it's 2 things. So let me write it. Calculation hinges on two games. Two facts. One of them actually I have proved. The first one is functional equation for Riemann zeta function. Remember, we wrote it as Zs equal to Z1 minus S, where this Z, as this is called the completed Riemann zeta function. Riemann zeta. And this is equal to pi to the power minus S over 2, gamma of S over 2, zeta of S. These factors are very, very important. They are called Euler factors at infinity. So there is a reason for that, but this completion also, there is a topological reason for that. This corresponds to compactification of integers. But this is not very important for us now. But this is called Euler factor at infinity. Anyhow, this is what we also derived. I mean, this I show that functional equation for theta function basically implies this, right? Okay, so this is then if you write it if you write this equation in terms of this, you have that. Indeed, pi to the power minus S over 2, gamma of S over 2, zeta of S is equal to pi to the power minus 1 minus S over 2, gamma of 1 minus S over 2, zeta of 1 minus S. This is the functional equation. Then what you do, you take a logarithmic derivative on both sides. Then take log derivative, maybe I'm okay here, log derivative on both sides. Then you need another fact, which I did not prove. Use the fact 2. So the second fact in these calculations is always like that. It gives you the constant term of the Laurent expansion of zeta near S equal to 1. So in other words, this fact is saying that zeta S is equal to 1 over S minus 1 plus gamma plus O of 1 minus O of S minus 1, sorry. This is cap O. Yes, cap O. S minus 1. So it basically gives you the first two terms of Laurent expansion. Terms of Laurent expansion. Zeta is equal to 1. Now what is gamma? Gamma is this Euler constant. So I believe this is defined to be sum. Okay, so basically this is limit of, as k goes to infinity, sum of 1 over n, and from 1, oh no, the other way around. Maybe it's this one. Yeah, maybe. I want it to be positive. So I think I just take sum 1 over n, and from 1 to k, minus integral from 1 to k, log x. Yes, log x. No, dx over x. Which is log x, log k. I mean, okay, so this term is just log k. Right. So basically, and this is equal to gamma. This is Euler's famous constant, gamma. So this gamma has been calculated by Euler and others. Euler, I think, is near 0.57 or so. Do I have it here? I hope. Anyhow, you can check in Wikipedia. I don't think I have it here, but I remember this is near 0.57. So let me put a question mark so that you check it yourself, so that I haven't told you a lie. Anyhow, so this is gamma. So basically, this says that, well, this diverges, but the way it diverges is like log k, and then there is a constant term. And this constant term also appears here. Okay? So you use this, because when you log differentiate this, then you want to multiply by 1 minus s on one side to get rid of the divergent part on the other side. And then you need this sort of expansion of zeta in order to compute this term. And then I believe you also need duplication formula for gamma function. Is it reflection formula or duplication formula? Maybe duplication formula. Again, gamma s. In any case, you put these facts together. It's a kind of one-page calculation, but after, it's a straightforward. This comes out that indeed zeta prime at 0 is equal to minus 1/2 log 2 pi. Yeah, minus 1/2 log 2 pi. So the corollary is that yes, I mean, then this determinant prime of not the circle, but this zeta is, so yeah, I mean, basically, so let me write it like this. Determinant prime, you see, the operator that we have has eigenvalues now 1, 2, 3, 4, so on, not without multiplicities 1, 2, 3, which is equal to infinite factorial. So this is equal to exponential. So this is basically equal to root 2 pi. Okay, yes. So we got this beautiful formula that infinite factorial is equal to root 2 pi. This is a nice formula, right? So infinite factorial is root 2 pi. I remember I gave a talk for undergraduate once. This was in the title. The title was why infinite factorial is equal to root 2 pi. So that talk, that pizza seminar talk, attracted the most number of students. So they were all curious to know. I thought I could prove it, but at the end I couldn't. I just gave some elements. But this was because I was very, very ambitious. I wanted to do much more than possibly could do. But anyhow, so this is something that. One more thing, we also need to know zeta of 0 to be equal to minus 1/2. Zeta of 0, it's also, there are these videos on YouTube you can watch. People prove it, all kinds of things, why 1 plus 1 plus 1 is equal to minus 1/2. Right? So that's what what they mean. They give all kinds of phony proofs of this, but the real proof again comes from functional equation. You actually need this in the proof. This also follows from functional equation. Okay, so yeah, so functional equation and ideas like that are quite powerful to give you some special values. Okay, so this is determinant, essentially, I mean, up to some factor here, which doesn't matter, is determinant of the Laplacian and the signal. So now we want to move to a next example, which is flat torus or elliptic curve. So let me do that as well. Are there any questions? Okay, so let me now move on to the next thing. So this is determinant of Laplacian. Flat torus. Okay, so this torus here, M, you know, we just think of it as R mod gamma. Sorry, R2 mod gamma. We can think of it as C mod gamma also. But gamma now is the lattice Z times 1 plus Z times tau. Well, this tau belongs to C and is such that imaginary part of tau is positive. So we think of tau as defining the lattice for us like this. So one vector for the lattice basis is 1. The other one is tau. Okay, in the upper half plane. And so here is the lattice. This is one fundamental domain, and then you can just continue. You pave the whole plane, all C by this, and then this is, of course, plus flat metric. Okay, so flat metric induced from R2, right? I say C. Well, I mean, in this case, I'll just take, I can take the metric. Okay, so this was dx squared plus dy squared. Okay, so that's the metric. So this is this example, this flat torus in literature, I mean, of course, is known also as elliptic curve. And yes, that's elliptic curve. I mean it's a Riemann surface. It's a Riemann surface in technical sense of the word. So it means it's a complex manifold of dimension 1. In complex dimension equal to 1. you can show that this is the only compact complex manifold of dimension 1, which has genus 1 or Euler characteristic 0. So the fact is that, so I mean, the way that we wrote it here is not accidental. There is something very fundamental about this presentation. Any compact Riemann surface of genus 1 is of the above form. For some tau. The tau that you get is not unique, but we know exactly what is the freedom, how much freedom you have in choose of tau. And it's not relevant for us right now. So, okay, now, then this gives us this Laplacian data. We can think of it as this operator ddz times ddz bar. You can introduce complex parameters here. I mean, this ddz, of course, is 1/2 ddx minus I dy, and ddz bar is 1/2 ddx plus I dy. And here I have to compensate by putting 4. So this is equal to dx squared plus dy squared. But I need minus because I want to minus this guy. I want positive Laplacian, so it's just minus this. So this is the Laplacian you want. So we already know the eigenvalues and eigenfunctions of such operators for general tori. So let me write it down. Eigenvalues and eigenfunctions. So we know that they are labeled by the dual lattice, right? Or labeled by dual lattice. Now, computing the dual lattice of this is not difficult because you know that you have to take one vector orthogonal to this, and you compute its length by knowing that the inner product with this has to be 1, and then another vector would be, so the two vectors, b1 and b2, are going to be, the b1 is orthogonal to this, and its length is determined by inner product with this to be 1. b2 is orthogonal to this tau vector, its length is determined by inner product of this to be 1 again. So once you do that, then you get some explicit formulas. I believe b1 is going to be equal to 1 over imaginary part of tau I, as I said over there, is along I. And b2 is tau, okay, is I tau over imaginary part of tau. Of course, I makes sense because when you multiply by I, you rotate it by 90 degrees. And then if you divide by this positive number, imaginary part of tau, then you have taken care of, you know. So this is the basis for, so this is lattice basis for gamma star. Okay, so now okay, so now I mean, eigenvalues and eigenfunctions as I said, I labeled it like this. So now lambda g, the eigenvalues are, these are the eigenvalues. This is minus 4 pi squared. Yes, norm of g squared, absolute value of g squared, which is plus, sorry, 4 pi squared. This is going to be equal to of this form, so it's going to be times absolute value of m plus n tau squared. If you square, an integral multiple of this plus integral multiple of that, and then square it, you get this quantity, imagine m plus n tau squared over absolute value of m plus n tau squared. Good. No, the other way around, sorry. No, this is imaginary part of tau squared, sorry. Yeah, imaginary part of tau. This is a positive number anyhow, squared, right? So in any case, the spectral zeta function is a sum so this is ZMS is equal to sum over Z2 4 pi squared power minus s, imaginary part of tau to the power 2s divided by absolute value of the length of n plus n tau, the power 2s. This is basically what? What is it? This is sum 1 over length of lambda g squared g belonging to gamma star, right? The eigenvalue that corresponds to the point in the dual lattice. What am I doing here? This is over S. Sorry, this is just over S. That's the spectral zeta function, right? This is the one, but if you use this information, so we know that this function, whatever it is, it's this prime again means that we are deleting the zero here, and then both cannot be zero. That's all it means. So this has an elliptic continuation. Of course, has a pole at s equal to 1, but then it's analytic on c minus 1. Analytic extension to c minus 1, right? And what we are after this quantity. So this problem is quite hard. It's much harder even than the corresponding problem for the zeta function, the one-dimensional case. But the strategy for the proof is to some extent similar to that. In fact, these sums were considered in 19th century by Kronecker. So Kronecker in 1860s, I believe, introduced this sort of real analytic Eisenstein series. So the one that we need is closely related to this is the following. It's this function E of tau and S. So what is E of tau and S? Yes, E of tau and S is sigma prime. Imaginary part of tau to the power S divided by absolute value of n plus n tau to the power 2s. Remember again, here is S, real part of S bigger than 1. Yes, this is holomorphic originally, that and imaginary part of tau positive. So you see, this is closely related to this, except that it doesn't have this factor, 4 pi squared to the power minus s. And it's s here, although it's 2s here. But they are quite related. They are very similar to each other. So this is real analytic Eisenstein series, because we introduced Eisenstein series as part of this story of elliptic modular forms, but they are holomorphic functions, but this function is just positive. And I mean, this is real analytic function. It's not, okay, I mean, at least, you know, for real parts of S positive, I mean, otherwise. This could be also holomorphic if this is, you know, if you go into it. But in any case, this function, so Kronecker showed that this guy has analytic continuation also. To C minus 1. The way we proved analytic continuation here was by knowing that this is actually zeta function of a surface and using heat kernel expansion. Kronecker perhaps did a similar thing, but not in this geometric language. He must have just pulled out the right estimates. I mean, I haven't looked at this proof actually. Must be, I mean, must be much more difficult than the proof that we saw here using Mellin transform. Now, then he proved the result about this function, which is similar to this Taylor expansion of zeta at s equal to 1. Okay, so first of all, he proved that, I mean, there are two things. First of all, functional equation. A functional equation for his for E tau S. I believe the functional equation is just that the value of the two things on two sides are the same. So E of tau S, yes, is equal to E of tau 1 minus S. So this already looks like a completed zeta function somehow. I mean, there is this factor here. Anyhow, so we have this thing. That's one thing. And the analog of the second fact that I just mentioned, namely the Laurent expansion near S equal to 1, is called Kronecker's first limit formula. So let me just, it's a very famous formula in number theory. This is called Kronecker's first limit formula. So what he observed and what he proved is that if you expand your function near S equal to 1, you have the following expansion. You have that E of S is equal to pi over S minus 1. First of all, the residue of this function, there is a pole, of course. I mean, here you can see at S equal to 1, there's a pole, but the residue is pi, and then the constant term is minus pi log of, yes, 4 imaginary part of tau, absolute value of eta tau to the power 4 divided by exponential of 2 gamma prime to 1. Okay. So everything here is clear except what is this eta function. So this eta tau, this is Dedekind's eta function. And this is another modular form, although I believe this is not an integral modular form, integral weight, it's a half integral weight modular form. Again, just let me write it, Dedekind modular, I mean Dedekind eta function. This appeared in Chronicles work. I believe Chronicles work was most probably before Dedekind. But anyhow, maybe Dedekind just studied this carefully and then proved a lot of results. I don't know. So this is Dedekind eta function. So what is eta of tau? That's equal to q to the power 1 over 24 product of 1 minus q to the n from 1 to infinity. Okay, well, as we had q is this Jacobi parameter is e to the 2 pi I tau, right? Imagine part of tau positive. Absolute value of q is less than. I mean, this infinite product is definitely convergent in the disk. I mean, in the open disk in the interior. So it's a holomorphic function here, or if you want, the function is holomorphic in the upper half plane. If you think of it as a function of tau. Of course, this q, you have to replace it by this one. So this 1 over 24 factor should not bother you. Although, yeah. So this is the Dedekind eta function.
Could I clarify something?
Yes.
What is the exponent of q? 1 over 2 something?
24.
24, okay.
Yes. Yeah, this the number 24 in all this business is very, very important. So, I mean, yeah, people have written about this, but maybe we should not discuss it now. But it's an important number that appears in several places. Yeah. So this is the expansion. Of course, I mean, this is wrong. plus, I should say plus, well, O of S minus 1, right? Because, I mean, this is not a simple, I mean, this is not a polynomial. I mean, this is not a, you know, Laurent polynomial plus O of S minus 1. Okay, so this is the constant term. Okay, so the strategy of the proof now is like before. We take log derivative of this guy with respect to S on both sides. And then you use, this is product of these. And then we use this information to eventually get the result about the derivative of this zeta, I mean, of this e function at 0. So the formula that you get at the end is that, I mean this, I'm not, okay, so you get that prime. Okay, so the formula that you get is this one. Yes, this is correct. That prime of delta 0 is equal to 4 times imaginary part of tau, which is a positive number, absolute value of eta of tau to the power 4. Now, what is delta 0? So this delta 0 is, is different from original delta. But it's conformally, but the metric that we are using here is conformally equivalent. You see, the function that this calculation gives is basically log derivative of, is the derivative of this function at 0. But this function is not exactly the spectral zeta function for our original elliptic curve, right? So we have to modify that a little bit. And the modification is not so bad. So what you do, you just replace the metric conformally. So change metric. Our metric was absolute value of dz squared, right? So this is dx squared plus dy squared conformally to 1 over imaginary part of. You just do a little bit of constant rescaling by the imaginary part of tau. That's it. Okay. So, as a result, so little exercise is that the area of the torus that you obtain by this method is going to be 1. Because the area of the original torus, 1 and tau, its area is imaginary part of tau, but the area of this one is going to be 1. You know, we have this 1 tau. And this is the original one. Under the usual metric, the area is equal to imaginary part of tau. You have to take cross product of these two vectors and do something. Maybe it's cross product the area or half of the area. Yeah, it's twice the area cross product. Yeah, it's area of the parallelogram, I believe. Anyhow, so you get the area by doing simple calculation, but then this area is actually 1. Okay, so this is the one, and if you calculate Laplacian for this, then you get that in fact delta 0 that we are using here is exactly minus 4 times imaginary part. Oh, so sorry, delta 0 is it comes out to be minus imaginary part of tau. Sorry. D2 dz bar. Why don't I have a factor of 4? I believe I must still have a factor of 4. Oh, no, there's a 4 here. Okay, so this is already taken care. Okay, so this. So, I mean, if you want, you can go back and calculate the determinant of delta, original delta, but this I didn't do, so you can write it in terms of this guy, but this is the determinant of very closely related. It's just a multiple of that. So the essence of this story is that, yes, Kronecker's second limit formula plus functional equation gives us the value of this regularized determinant. So determinants of this sort of things that are related to number theory has been computed in many cases. These limit formulas have been extended, and it leads to some very interesting problems in number theory, but we don't discuss it. So this is, I think it's a good time to stop, and then we come back in 5 minutes to give a couple more examples. So maybe I just, all right, so now this is example 3. So this is Polyakov's conformal formula. So this goes back to Polyakov wrote 2 papers in 1982 or 83, I think, maybe 81. So this is around 1982. That kind of restarted string theory. So this was for bosonic strings. Anyhow, so we don't need any of these things, but this is the title, more or less, of the paper. So, but it really boils down to some determinant calculation. So now let mg0 as we had. So this is a closed connected. Now we are looking at two-dimensional, only two-dimensional surfaces, two-dimensional Riemannian manifold. Okay, so this is okay, yeah. So yes, okay. So of course, I mean, from here, then we have like that prime of. So let me put this delta G0. Of course, I mean, this is minus zeta prime of delta 0. I mean, I put it like this, delta G0 at 0. So now I'm changing my notation. Well, this zeta G0 really means zeta of M and G0. Just to lighten the notation, I'm using this new notation for zeta function, spectral zeta function with respect to this metric G0 now, not, okay. So this is one quantity like that for this Laplacian that we define and exists. And so now let us change the metric in a conformal way. Conformally to G equal to e to the 2u G0. For u, of course, is from M to R, is just a smooth function. So, I mean, this is called the conformal factor, and this U sometimes is called, I don't know. I mean, this e to the 2u is called Weil factor. This U is a dilatant field, or maybe this one. So it doesn't matter. Any conformal change of metric, you can always write it like this for some appropriate U. This is, so G and G0 are called conformal metrics. So, okay, we have this log det for G. Now we want to look at log det for, for G0, we want to look at log det for G. So this gives us this log det G, right? So that's, now, this log det is highly, as we saw, even in the case of flat torques, in the case of this circle, which is round metric, we saw that it's a very delicate matter to compute log det. I mean, derivative of spectral zeta is 0. So you can imagine for a general metric, and this is surface hydrogens, is impossible to know actually. I mean, what it is. But what Polyakov noticed is that the difference of these two numbers can be computed explicitly in terms of the data that you have. And that's really an amazing thing to know. So, so Polyakov's formula is this. Is that the difference between these two numbers, log det delta G, yes, minus log det delta G0 is given by minus 1 over 12 pi integral norm of gradient of u squared plus k G0 u d volume G0. Okay, so you integrate over the surface with respect to volume form of the original metric, this quantity. Now, okay, so this has to come down. So k G0 is Gauss curvature of the metric G0. And of course, kg, this is, I mean, it's conformally perturbed, but the Gaussian curvature changes drastically in general, right? So this is this same. Okay, so this defines this part. U, of course, is a function. This is the two form. Now, what is this? This is the gradient of the function. So it's a vector field. To compute this gradient, we also need a metric here. And for this gradient here, you can use, we have to use the original metric. So everything is in terms of the original metric. And you compute this quantity. That's this conformal, that's this conformal anomaly formula, because it gives you the difference between these two numbers, or basically gives you a log of the quotient of these two things. So this is remarkable because we don't know any of them, but we can compute the difference. So this has some cohomological meaning into it, right? It's like in cohomology. Okay. So now let me tell you a bit of idea how to prove this, because it really uses two main ideas. So ideas of proof. So this is One idea is there is a famous formula that goes back to Gauss. It computes curvature of this metric in terms of this metric, basically. There's a famous, yeah, it could be Gauss. I mean, Gauss is, I just write it like this, formula for Gaussian curvature. It just says that, yes, Kg, the Gauss curvature of this conformally perturbed metric is e to the minus 2u Kg0. This is the original Gaussian curvature minus Laplacian of G0 of the function u. So this is a beautiful formula that relates the Gaussian curvature of two conformally equivalent metrics to each other. You can try this as an exercise even because you know the definitions. I mean, so proof exercise, it's an interesting exercise. It's not so trivial, but okay, so yeah. It takes some, it's a very good exercise for geometry of surfaces to do this. I mean, it's fundamental. So one of the things that you use is this one. Of course, the second one is to write down zeta in terms of this hit kernels, right? So let me write it here. Second idea. Zeta, okay, so zeta G0 as, remember this was 1 over lambda I G0 as lambda I different from 0, and this is equal to 1 over gamma of S. Remember, we use Mellin transform 0 to infinity, exponential of minus t. Well, I mean, there's a trace, exponential of minus t Laplacian G0 minus 1 times t to the s over t G0. And for the second one, you have zeta Gs, of course, is again 1 over lambda. I just write tilde maybe s lambda I tilde different from 0, but then this is equal to 1 over gamma of s integral 0 to infinity trace of exponential of minus t delta, this time g, the Laplacian with respect to the metric g, minus 1 t to the s over t dt. But then we can use the asymptotic expansions. I mean, the asymptotic expansions tells us that I mean, we get zeta G0s. If you expand it like this, you get 1 over gamma s integral 0 to infinity. Now, this number, we know that this is 4 pi t to the power minus n over 2, but n is 2, so this is minus 1 times a0 plus a1t plus a2, 1. Now this A0, we know what it is. A0 is volume of mg0. And A1 is kg0. Kg0, yes, is I mean, it's basically integral of kg0 the volume g0 over n. Right, of course, we can write the same thing for the second one. Then you have to do kind of variational trick. I can prove it next time, but let me just give you the idea if you want to read up. So variational proof is that you see what you do, you introduce a second parameter. We have this metric G, right? This was equal to e to the 2u G0. You introduce a parameter H here. So you get families of metric GH. So H belonging to interval 0, 1, which is e to the 2h u G0. Now this family is such that at 1 is G, this is just G, and at 0 is G0, because H is 0, this is G0. So, okay, so you have put your conformal perturbation into a family in the space of metrics, into a curve. And you look at this with respect to GH, and you start differentiating this. I mean, what we are interested in is really zeta prime. S, right? The derivative, and then at s equal to 0. But now you have a two-parameter family of functions. It depends on s and depends on h. So let me put it like this: zeta of hs. Basically, this is equal to trace of Laplacian of gh. H to the power minus s. Right? It's this one. And so you have two parameters to play with, and you take and then at one place you have to switch the orders of these things, and then you have to show some terms or boundary terms, but the main trick is going to be played by this Gauss formula. And use Gauss's formula. Okay, so it's not very difficult if you know you have to use Gauss formula. And of course, this was a standard. So this was done by Polyakov in like, I believe, half a page or something. Very quickly, he just, but the formula had amazing ramifications. I mean, this formula has amazing consequences for early stage of string theory and for also for geometry of surfaces, because now we are up. I will show that how this result was used by Osgood, Phillips, Sarnak to prove uniformization theorem. So the proof that they gave seems to me actually, of course, uniformization theorem was known for a long time, but even the proof that gave, there was a similar proof using different ideas before that, using PDEs, but they gave a proof. So maybe that's related to your question, actually, because they consider this determinant as a functional on the space of all metrics, And then they study the critical points of this functional. So this plays a role. So it can be used. So yes, for geometry of surfaces can be used to prove, for example, uniformization theorem, which would be a natural proof. Okay, so I think we can stop now, but